Okay, so who here has done spectral line observations with any kind of telescope? What about radio telescopes? What about single dish radio telescopes? Okay, so we're winnowing down. For single dish spectral line observations, there are some things you have to consider about your strategy to take away things like baseline structure, the stray noise from the atmosphere, etc. So we're going to talk about that throughout this talk, and then talk about at the end a little bit about calibration, like Dave was mentioning. So you've seen what Dave went through, basically confusion with continuum observations, 1/f noise, definition of telescope temperature scales and efficiencies. And I think that one slide that Dave showed that showed TA prime, TA star is a really useful reference. So I would recommend that you pull that off of the PDF because very few places is that all contained in one little spot so clearly. So we're going to use some of those temperature scales through this talk too, but we're mostly talking about atmospheric opacity, spectral line observations, frequency versus position switching, like we already got into a little bit, and then some on instrument calibration. So first off, with opacity, this is something that's familiar to all of us, right? Most of the atmosphere of the Earth is opaque to electromagnetic radiation from space. In the radio, we're fortunate that we have this big gap that light can get through. But even in the radio, when radiation reaches the ground, it has often been attenuated, refracted, or altered in some way, right? And we want to be able to account for that. Depending on the frequency, these corrections may be fairly significant. So you've already seen this picture, this cartoon earlier today. Here's where we live, down here in radio telescope land. And you can see that compared to most of the electromagnetic spectrum, we have it pretty good. So gamma rays, X-rays, and UVs are pretty much entirely blocked from the atmosphere. There's a nice window here for our optical friends to see optical light, and in fact, why our eyes function like this, right? We can see optical light because that light comes down from space and we are allowed to see that. So we've evolved in that way to be able to be sensitive to optical light. But the mostly unblocked regimes are in radio and optical. And compared to the optical width here, the radio width is very large, right? We cover orders of magnitude in wavelength, whereas in the optical, it's about a half order of magnitude, right? So zoom in here. I thought radio was supposed to be immune to atmospheric absorption. What's up here? Not cool radio, not cool. So above about 10 gigahertz, the atmosphere does start to be important in the radio. And so you do have to take care of that. So you were supposed to be different radio. You're not so different after all. With the Green Bank telescope, we can trace basically from down here-ish up the whole way to the far end of this red line, out to about 116 gigahertz or so. So for much of the GBT's spectral range, we have to take care of atmospheric attenuation. This is another way to view that last plot. Instead of transmission through the Earth's atmosphere, now we're looking at tau. So you can think of those as inverses of each other, basically. We also saw, I'm going to flip back to, we saw that there are two walls here, right? There's this one at high frequencies, and then there's this one at low frequencies around 10 meters or so. So that lower limit at about 10 megahertz is where astronomical signals are reflected back at us from the ionosphere. So anything that we transmit is reflected back to us. Anything from space is just reflected back out into space. So we are not receiving those signals. It's not that they're being absorbed, they are being reflected from the ionosphere. So we cannot do astronomy on Earth lower than 10 megahertz, right? Just can't see those signals. And then the upper limit of about 1 terahertz is where atmospheric molecules define the radio infrared transition. And again, you can't do that from the ground because the atmosphere is too thick. You have to go to mountaintops, you have to go to Chile, for Alma, or above the atmosphere, like Sophia flew above most of the atmosphere, or out into space. So realistically, the atmosphere is not perfectly transmissive at any frequency, but there are some that we have to take extra care for, and where the atmosphere will add significantly to the system temperature. So these are measurements from Green Bank of the tau from this site, going from basically the lower limit of our observations up to the upper limit of the observations. So the black curve here is expected to be the total. And actually, I don't think that these are observations. I think this is a model. I believe so. I'm looking at Dave, but I'm not sure. So you can see a couple features here. Anyone know what this feature around 22 gigahertz is from? Water, right? Anyone know what this one around 50 gigahertz is? Oxygen. And then we have, what about over here? Again, that's oxygen, right? So if you've ever done ammonia observations, you have probably noticed that you have to do ammonia observations when the weather is really good, right? And it's because water in the atmosphere is going to blow your system temperature away around 22 gigahertz. And then we just don't try in this range, right? It's diminishing returns. We really can't get anything good up there. So these are measurements that show how tau varies with frequency in Green Bank during the summer. And again, I guess the answers that I asked you for are written there exactly. So water and oxygen lines are the limiting factor at some frequencies. We also have hydrosols, dry air, adding a bit, but less significantly across most frequency ranges. Hydrosols important across the entire upper range. So. Now, we've said that the atmosphere must be corrected for. How do we do this? Well, it depends on where you're pointing in the sky, right? You're looking through the least amount of atmosphere. If you look straight up, you are looking through one air mass. As you point towards the horizon, you are looking through significantly more air. There's significantly more atmosphere that you have to account for. And so I've included a couple of equations here for how you can calculate how much air you're looking through. This one is a bit more exact. This one's good enough until you get down to about 15 degrees. And if you plug in zenith angle of 90 degrees, which would be pointing out towards the horizon, you'll find that the air mass at the horizon is about 40. So you're looking through about 40 times as much air, 40 times as much atmosphere if you're looking towards the horizon than straight up. So for high frequency observations with Argus, with Mustang, we pretty much say you don't want to do that below about 30 degrees or so. The higher your source is in the sky, the better, as long as you're avoiding straight up at zenith, because then you get weird telescope motions where we can't track fast enough. But aside from that, you want to observe high frequency objects above about 30 degrees. Right? So in here, Z is the zenith angle, so the angle from straight up, down, and here L, that's the elevation, so you could say 90 minus the zenith angle for that equation. So when you have high opacity, if you're observing above 10 gigahertz or so, you probably want to do something like this to correct your data. So this is what you measure, and then you're multiplying by E to the air mass times tau. Right? So straight up, again, A would be equal to 1. Tau would be equal to something that we can give you that you can measure at various sites. So here in Green Bank, we keep track of tau versus frequency. There are ways that you can go into the system and say, hey, for this time at this frequency, tell me what tau I should be using. And so that is something that you're definitely going to want to correct, because let's say you are looking at a high frequency source near the horizon and you see a pretty bad detection, but you see something there, you might think it's not that bright. Well, you're looking at high frequencies through a lot of air. That might be a whopping bright line. It's just being attenuated a lot, right? And so any questions on this? You saw this from Dave's previous talk, TA prime. Again, TA prime is the temperature corrected for the Earth's atmosphere. Yeah.
Just a quick clarification. You said the reason that we don't want to point straight up is just because of the engineering difficulties of looking up, not because that's bad for the.
Correct. Yeah, so for the GBT, we have something called the keyhole that gets bigger at higher frequencies. So it's basically that the telescope just can't move fast enough to keep up with it, because the GBT is, let's say I'm pointing at the horizon, I'm tracking a source roughly. Whenever I get to here, the GBT can't bend backwards. So it has to turn around to keep tracking that way, right? And so it just can't turn around fast enough to keep you on your source the whole time.
Okay.
This is common to every telescope, I mean.
Yeah.
Not only GBT.
Correct. Yep.
How is the zenith capacity?
Yes, tau naught is the zenith opacity. Yep. Any other questions here?
So the 140 will not have that problem because aiming to so that the Senate. So
So the 140 foot would not be
will not that
right. It's just moving in one axis, right? So that would be easier for that telescope to track something through zenith. Yeah. But all modern telescopes essentially are azimuth elevation design. Any other questions here? Cool. So as we mentioned, as we harped on, the atmosphere is important at high frequencies. Here you can see the precipitable water vapor. We showed this plot earlier this week in millimeters in the atmosphere. So if you were to point straight up, how much water are you looking through between here and space? So this red curve is for Green Bank and black is a cumulative percentage. So basically just adding up each of these things across. You can see that our peak is around 5 millimeters. So we have some really, really good high frequency weather, mostly in the winter, whenever water or vapor is frozen out of the atmosphere. But we have a pretty wet tail. So the other day when we looked at this, we looked at what the value was and it was somewhere around 30. So we were sitting right in the middle of a thunderstorm at that time. Precipitable water vapor was high. Right? So this in general is the summer. This in general is the winter, and that describes why we have high frequency observations here, mostly in the winter. So some of these days are comparable to ALMA weather. We could do potentially 1 millimeter observations here in Green Bank, but you would not have nearly as many chances to do that observing at 1 millimeter or 300 gigahertz than you have at a site like ALMA. Right? Okay, so we've gone through atmospheric opacity. Let's talk about different switching methods, but first we're going to talk about why you want to do these different switching methods. What is a telescope seeing when you point it at a source? Well, we want to measure the source temperature. We want to know what is actually truth about our object out in space, but what we are actually measuring is TA, the antenna temperature. And the signal that you're seeing from the GBT is a combination not just of what your source temperature is, but all these other things that are adding themselves into the system. So the system itself adds some heat to the measurement. We'll call that T instrumentation. And here we have a picture of the GBT and then a schematic of what the beam might look like. Right, your main beam is going to be stronger. Your side lobes are going to be pretty far down. And we're looking at some beautiful H2 region over here. So not only do we have the instrumentation adding noise to it, we have spillover. So there can be signals maybe from the ground, nearby buildings, etc., that are adding temperature into our receiver. We also have radiation from sources in the sky that we just don't care about, right? There are all these background radio sources. There's that confusion measurement that Dave was walking us through. There's the CMB, for instance. So those are just extra noise for us. We don't care about those. We want those to go away. We care about our source temperature. So basically, we care about this first term. We could not care any less about any of those other ones, right? So we want a way to get rid of all of that. In essence, this is what we care about, all that in red. is everything else, the T from every other part of the sky and our local environment, including the receivers. So rather than try to carefully model each of these and say, well, I know the CMB is 2.7 Kelvin. I know the atmosphere at this time and at this frequency is 15 Kelvin, something like that. We can just lump all of this together and call that T off. And we're going to find ways that we can just measure all of these together and subtract it from this long equation to just give us the T source. So in practice, it is considerably easier to eliminate the source by going to an off position where we're measuring all of that other stuff in red. And the ways that we do this are through different kinds of switching. So we have position switching and we have frequency switching mostly that we're going to be talking about. So you saw Dave mention off positions and also mapping. I'm not going to talk about mapping here because he'll cover that in a later talk, but it's going to be the same types of stuff we're looking at. So go off, King. There's a joke. Again, we're going to hit on position switching first. So for position switching, we are going to go and look at two different parts of the sky. We're going to look at our object, and then we're going to look at something that is not our object. You mentioned nodding also, where you can just nod the telescope between your source and if you have two beams, so you are always in one beam. We're going to get deeper into that in a second. But quickly, the advantages and disadvantages of position switching first. So position switching usually yields pretty flat baselines, and it doesn't require you to know very much about your source in advance. You need to know a little bit about the region around the source so that you're not going from your object into another bright object. But you can do that by looking at sky catalogs or maps from interferometers or single dishes of what the environment around your object looks like. What I say whenever I say you don't need to know very much about your source is that you don't need to know what velocity it's traveling at. You don't need to know what spectral lines it contains, etc. So that's an advantage. Disadvantage is that you do need to know a little bit about the environment around it typically. If you're looking at a source in the galactic plane, you can usually just go far away from the galactic plane and that's good enough. But still knowing a little bit about the galactic plane existing for you to go off of it. Another disadvantage is that it could be integration time intensive because you are not on your source the whole time, right? You might only be on it half the time. So that decreases your on source time by a factor of 2, meaning you might need to double the length of your observing program. Another thing, slight disadvantage, non-uniform illumination can cause differences in your baseline. So let's say your target that you're looking at is a really, really strong source. It's bringing a lot of power into the system. Your baselines might look slightly different than if you go off source and you're looking at a very faint part of the sky. That extra power that you're pumping into the system from your bright object might be making your baseline a little bit different in your on than in your off. What do I mean by this? Okay, so here are two actual scans. This is an on scan of some galaxy made by Karen O'Neill, and this is an off scan. So can you tell me, anyone, where you think my astronomical source is in this on scan?
Well, there is the spike.
You think it's one of the spikes? So you see the spikes in all of them, right?
Just to the right of that middle spike. that looks like
You see a little bump right there? Yeah, so that is our on source, or that's our astronomical object. So what we would do is we have our on emission, we have our off emission. Do you see that little bump over here? No, it's not there. So we're going to subtract on minus off to get rid of all of that extra instrumental noise and everything else from the sky. And when we do that, we see this. So our baseline is maybe a little bit funky here. We might want to fit a polynomial to that baseline to flatten it out. But you see your actual object here now. And this is a very faint galaxy, fairly far from the Milky Way. Let's see, what is the velocity here? It's not listed. But Karen studies usually pretty distant galaxies. So with position switching, we are taking from our on source or on scan T source plus T everything else, subtracting everything else. And then with this simple math equation, we just have T on source, right? So we got rid of that garbage that was coming into the system and only have information about our source. Now, of course, there's still some noise here, but it looks much better and took all of those big wobbly baselines out from what we saw on this previous image. For your 20-meter observations, you will have noticed that you have some large baseline structure, right? For your maps, have you seen that? Yeah, so you're not, in most cases, doing an off scan. You're just basically looking at the on scan. And so for you, you might just fit some kind of baseline to this whole thing and subtract it from it. There are ways that you can do off scans, but for the mapping, unfortunately, you can't do that. So we can talk about that in your groups later. Okay, so that is a basic on-off scan. We'll introduce a little bit more about nodding. We've already mentioned it twice. You can only do this for receivers with more than one beam. And the reason that is the case is because you're going from, let's say that my fists are two beams of a telescope. I'm looking at Lexi here. So Lexi is currently being seen by my left beam over here. So I might integrate there for 30 seconds and then I might switch. And now Lexi is in my right beam and I still am getting off positions from this integration. So now this is off, this is on. Now this is off, this is on, right? So you are on source the entire time, meaning you don't need as much time in your full observing proposal because you're on source the whole time basically, but you can have some time to switch between those beams, right? The GBT still has to move. And so you might have a couple seconds there of downtime for each scan. Dave was also mentioning something that we call the sub-beam nod, that instead of moving the actual physical telescope to go between beams, you're just flicking the subreflector a little bit. And so that tends to be a lot faster than moving the telescope between beams. You're just changing the subreflector to do that same thing where you're looking between the two beams. Then. Is that clear? Nodding versus sub-beam nodding versus traditional on-off. Awesome. Let's see, drawback and pro tip, we already gave both of those. If you have the option to nod for a program, I recommend that you do that, right? Because you're saving time. Right? For some receivers, it's not possible. I've done a lot of work with X-band, for instance, that's only 1 pixel. L-band is only 1 pixel, so you don't have the option to nod. We are switching now into frequency land. So any other questions about position switching before we get there? Yeah.
So for my experience with the 40 foot, we under the drift scan, so we start with baseline, we get the source, but sometimes on the other side of the source, there's a higher baseline. That's caused by
I think for the 40 foot, that is likely an instrumental effect where maybe the gain is drifting throughout the observation. And so as you go across the source, your baseline just is at a higher level because your instrument calibration is changing slightly. But that's my guess for what that is.
Question.
Yes.
I don't know if this is kind of naive, but I guess how off is too off and not off? Like, you know what I mean? Like,
Yeah, really good question.
okay.
Because let's say your source is over there. If you say, oh, I want to get off. Oh, I know a good off over there. You're looking at an entirely different part of the sky. You're looking at a different part of the atmosphere. Things could be very different. So usually I've gone a degree or a couple of degrees away. You also don't want it to take a day for you to scan over that. You don't want it to take a bunch of time because then that's adding overhead. So usually I would say within a degree or so. If you can find really clean areas. If you are looking towards the center of the galaxy, a degree is probably not far enough because you might need to get significantly out of the galactic plane, depending on the species you're looking at. A really good question. Yep.
I don't, for the nodding, if you have the two beams, why do you even need to to move from one to the other? Because you already have one off and one on, right? Why do you have to have a second position? I guess that might be a dumb question.
No, it's not a dumb question. Why do you need two beams? There is going to be slightly different calibration between the two beams probably. And so by knotting between them, you take out that source of error as well. Is that sound good? Okay.
And you compare the two things separately or you put them together?
Usually you put them together. So we have routines that are already written where you would say, I have a knotting observation. I want you to grab that knotting observation data and it will do that comparison already for you using both of them. Yep.
So in each cycle, are you also switching polarization or are you staying?
So you would keep the same polarization. I mean, usually most of our dual beam receivers, well, some of our dual beam receivers are dual polarization. Some of them are only single polarization. So you would have the same polarization comparison between the two. For instance, Argus is single polarization, but every beam is the same polarization. So it's not like they're interlaced where you have XX and YY and XX and YY. They're all just the same. Anything else? Yeah.
So if we go back to the spectrum with this abstraction, why are the temperatures taken? What does that mean?
So this means that, yeah, the temperature that you read should not be negative. What you care about is the difference between the baseline and the peak. So usually for this, you would fit a baseline to it. So there can be slightly different baseline levels between your on and off, that if your off actually has slightly higher temperature for some reason, then you would get into negative baseline region. So in practice, what we would do is fit a baseline to this,
Okay.
subtract it, and it would bring this all up to 0. So this brings up another good point about calibration, about wanting to understand the actual true calibration levels, and we're going to touch on that here in a little bit too. Okay. We talked about frequency switch or position switching. Another method is to frequency switch. And there are different things that this is good at. So there are two types of frequency switching: in-band frequency switching and out-of-band frequency switching. And the names are pretty self-explanatory, but we'll go through each of them. So in-band involves keeping the telescope on the same source in the on position. So I'm pointing my telescope beam at that speaker right now. That is what I'm observing. It has, you know what frequency you're looking at, what spectral line you are looking at. So you're changing the electronics to switch your frequency setup instead of changing your position on the sky. So you are switching in your band pass where that spectral line appears. So you're using the LO such that you're shifting the line. Out of band switching is similar to that, where you're still changing your frequency, but for out of band, you're going from seeing your spectral line to having your spectral line be entirely out of the band pass. Now, why might you want to do this? Well, you're characterizing again this band pass shape. So you want to get rid of this band pass shape, and you also want to get rid of all of that other junk that is not necessarily as frequency dependent as where your spectral line is, right? Temperature from the atmosphere, etc. So advantages for frequency switching are that it is efficient, because in band frequency switching, you are always observing your spectral line. So you are on source 100% of the time. And it can be done very quickly. The system can switch between these two frequencies on the order of a second or a couple seconds. So the faster you switch, usually the better you're taking out these instrumental uncertainties. Disadvantages: one, it requires knowledge of your source velocity. You have to know where you're expecting to see this line in the first place, so that you can not accidentally switch this line and overlap it with another spectral line over here, for instance. Like, let's say that right there is a methanol line or something like that. Well, whenever I do the comparison between those two, I will have averaged that methanol line and your spectral line together, and then you just have garbage output, right? So you need to know a little bit about the velocity. And the system has to be stable enough so that your signal and reference spectra are essentially identical. We're able to do this mostly by just that fast switching. But if your system is drifting faster than second timescales, there are probably some other problems there, but frequency switching will not work very well for you. Now, look at this a little bit more in depth. As we said, this is very efficient. It's always on source. So we have our center frequency, and we see our bandpass shape here looks the same between time 1 and time 2. And we are just switching the electronics such that we change what frequencies we have here listed at the center. We're shifting our line from over here to over here in that observing epoch. We will take time 1 minus time 2 and time 2 minus time 1. It takes out the band passes, right? Time 1 minus time 2. You see these band passes were the same shape. So that subtraction gets rid of that large scale structure for both of these, right? And you have the positive of a line over here, the negative of the other line. So this is this line from over on this right side, that T2 line. This is that T1 line. And this is the opposite over here. So this is the T2 line. This is the T1 line. From over there, just negative, right? Because we subtracted it. And then we will shift these in frequency space to overlap this positive line with this positive line, and we will average those two together. Okay? So now you have a larger line in here that is the sum of this line and this line, but you still see these negative images over here from those negative lines over here. Right, so we're always on source. We have square root 2 gain in our sensitivity versus a position switched observation because we're observing for twice as long on source. Right? But what are some drawbacks that you could potentially think of if you have these negative lines over here that are going to be in your output spectrum? What, Yucca?
If there was like a really weak line there, it might be completely ignored by the negativeness of it.
Yeah, so if there's another line that you don't really know about, but your frequency throw made it such that you accidentally overlapped your negative line over that, you're not going to be able to see it, or if you do see it, its intensity is going to be wrong. Yeah.
This is done during the observation or after the observation?
After the observation, so you're saving basically these data, and then it's the reduction after the observation that goes back and actually adds them together.
Can they be mistaken as absorption?
Yeah, you can mistake them as absorption lines for sure. So those are some of the main ones I'm thinking of. Do you think that this would be good for an astrochemistry experiment? Why not?
You're looking for more than one line there, right? I mean,
Yeah, you're
you don't know
typically,
what you're looking for. So
yeah,
how
you
can
don't know what you're
calculate
looking for, right?
Yeah.
So it's a detection experiment. If you have these random lines popping up everywhere and random bowls on either side of them, you are not going to be able to interpret this. So for this reason, astrochemistry uses on-off observations. I have a slide here in a little bit about what each of these methods are good for. But first, let's talk about out of band. So out of band, the benefit is that it also eliminates your bandpass structure. The drawback is that you are only on source half the time. So if you are not worried about that loss in observing time, this is a fine technique for you. In practice, I have done in-band frequency switching only. But usually this is better at eliminating baseline structure than just trying to fit a polynomial or something to that baseline. and subtracting it away. Right? So it works the same. The benefit that in-band has over out-of-band is that in-band is on source for twice the time for the entire observation. So here is a little table about when you might want to use one or the other. So drawback of position switching is that it requires double the observing time because you are off source half the time, except for when you are nodding. So if you have two beams, you can get rid of that drawback. This is useful whenever you have broad lines over about 100 kilometers a second or so. If you have narrow lines in crowded spectral regions, right, because all of those positive narrow lines in crowded spectral regions, if you do frequency switch, are going to have negative components associated with them. You're just going to have a mess in your spectrum. Also, if you have significant RFI, position switching is the way to go for the same reason. RFI is going to show up as negative images as well, so you're going to have triple the RFI. And for all these reasons, astrochemistry wants to use position switching. Frequency switching is good because it can be very efficient. You're always on source for in-band frequency switching. And you want to use this when you have a narrow line in a non-crowded spectrum. So for CO observations at 115 gigahertz, most people use frequency switching. In places of the spectrum where you have only a few lines and you know exactly what to expect from them, use frequency switching if it's narrow. If it's broad line or if it's a crowded region, use position switching. Any questions here? Because we are going to move on from position versus frequency. Yeah.
This might be a naive question, but what are some actual examples of when you would have a narrow line in a non-crowded spectrum?
Yeah, so I've used it for, I think entirely for CO observations, CO, HCN, HCO plus. So these lines that are pretty much standalone in their frequency range or very, very bright.
Okay.
Right, and so there's nothing really comparable around them. And they're on order of maybe 10 kilometers a second or so wide, probably even less than that.
Okay.
So that's when I've used frequency switching. I've used position switching for all of my low frequency observations, where there tends to be a little bit more RFI and around X band, a little bit more of a crowded spectrum.
Okay.
So my recom observations have all been position switching. My molecular gases have all been frequency switching. Anything you want to add, Dave?
I'm just, well, certainly the higher frequency, the narrow lines of frequency switching, when you're doing the mapping. And because you can do on the 5 frequency switching, and so you always have your offs, where when you just people do galactic stuff, it's really hard to get an off. With CO, just like H1's everywhere, CO's everywhere. So you can do frequency switching is not powerful. The data quality is much better because you're switching faster and then it actually works really well. And like the chemists, like they would do position switching, as you said. That's what you do crowded spectrum.
Now, CO is everywhere. H1 is also everywhere, like Dave was saying. H1 is not a good line to use frequency switching for because it's so broad, right? Your frequency throw would have to be very large. And I don't know that I've ever seen people really do galactic frequency switching. You would? Okay, well.
What do you mean? H1 I guess it depends on where you're looking. I see what you're saying, because you're trying to cover the entire galaxy, then you have to be careful, but you tile maps at certain parts of the galaxy. I guess you definitely.
Yeah.
It's not. Because
just be careful.
The line widths are only 10 kilometers a second.
Be careful with it, right?
Yeah.
If you don't know exactly the H1 structure,
That's right.
and you can't if you can't get a wide frequency throw, then you might be interfering with yourself. I've even done this with CO observations before, where I didn't have a large enough frequency throw, and so I ended up getting my line looking like, so here was the main line, but then I didn't do enough of a frequency throw, so my negatives were like there, taking away from the peak. So it looked like I had a really narrow CO line, But really, it was just that I didn't set up things correctly, right? To make those negative bowls further away.
So you bring up a good point. If you're not sure what you're looking at or what you're gonna find, position switching is a lot safer than frequency switching. But there are some advantages to switching.
Cool. We are on to the last bit of this talk on instrument calibration methods. So up until now, everything we've done has been relative comparisons between one on, one off. I'm removing baseline, right? But I don't really have any knowledge of the true flux of my object, just the relative flux between an on and an off measurement. So how do we get that, right? How do we go from arbitrary counts to something with physical meaning, watts, ergs, Janskys, etc.? The three main ways are going to be observing targets of known brightness, right? Quasars, planets, etc. Number two, introducing noise of a known amplitude. You've seen this through your 20-meter observations. You've seen the noise diodes there. Or like Dave was talking about in the last talk, observe something near the telescope of known temperature, hot and cold loads. Again, all of these are involving looking at things that we know the brightness of so you can compare to your observation. So how do we do absolute calibration? Well, our absolute calibration here in Greenbank is tied to Mars via WMAP. So we have models for what the brightness of Mars should be at different positions in its orbit based on how much sunlight is bouncing off of it, right? Based on where the Earth is comparatively. So we can observe Mars and say, okay, we have models, we know very, very accurately what the brightness of this object should be. Let's look at it and let's bootstrap that calibration to what we know it should be, right? So we can get down to about 1% absolute calibration accuracy with Mars below 20 gigahertz and a little bit worse, 3% or so above that, between about 20 and 50 gigahertz. So up here, all of these plots in black are the model of what we think Mars, black is the observation, what we observe the brightness to be, red the model of what we believe Mars should be there. And so you can see across all of these days, these are days on the x-axis, and intensity or beam temperature on the brightness temperature on the y-axis. These models match up very well with what we actually observe to be the case. So this is absolute calibration. For your observations, sometimes people do, and it is good practice to occasionally observe planets, right? Mars, etc. Mostly, folks will observe standard calibrators. So our absolute calibration is based off of Mars, but at the start of your observation, you may look at a bright quasar and say, okay, I know what this bright quasar intensity should be. And these are all pretty well known. Some of them appear to be drifting with time, so we will occasionally take calibrators off of the list of recommended objects to look at. But here's a standard calibration plot from Rick Purley at the VLA. And the VLA and ALMA maintain lists of excellent calibration sources with very precise fluxes across our frequency range, essentially. So I would say it's really good practice to observe one of these quasars. Usually you'll do a pointing peak focus on one of these quasars at the start of your run to make sure everything's going well, but you might also want to do an on-off or something on one of these objects. Again, to make sure that you can go back later on and say, well, this is the intensity I got for my object. I observed this quasar and I saw this intensity, and that really matches what it says it is in Purley and Butler. So my calibration for my science observation is pretty good. Right? This is always good practice. We also, with the GBT and the 20 meter and the 40 foot, use noise diodes where we are injecting noise of a very well-known amplitude into the system and then scaling the rest of the temperature scale appropriately. So let's say we know that we have, and someone did this example the other day, let's say that we know that this is a 1 Kelvin noise diode and the strength of this line is 3 times the height of that noise diode. Well, you know then that the intensity of this peak is 3 Kelvin, right? It's 3 times the noise diode height. So all of the GBT receivers, except for the highest frequency ones, the 4mm, Argus, and Mustang receivers use noise diodes where they are injecting the signal into the path. And so if you get GBT observations, it will come out calibrated already for you based on those noise diodes, unless you're using W-band or Argus. And in that case, we use a different method. Before we get into that different method, for the 20-meter and 40-foot, we turn the noise diodes on at the start and at the end of the observation. So we are just basing our calibration on that start and end point. So you can imagine if you have a really long 20-meter observation and you're just injecting those noise diodes at the start and end, that calibration may drift a little bit throughout. So for the GBT, what we do is just flicker them on and off on the order of seconds, right? Under a second. And so there is the equations for calculating the system temperature for 20-meter versus the GBT. Questions about noise diodes? Yes.
I have a question about calibrators. Are standard calibrators used when like Mars is too far or something? Or it seemed like Mars had it covered, so I was just like, what are the standard calibrators for?
So there are standard calibrators across the entire sky, which is their benefit. So regardless of when your observation is scheduled, you can observe one of these calibrators. I mean, we have a great list of dozens to hundreds of them based on the frequency range, and pretty precise values for what they should be. Mars is also slightly extended, right, depending on the frequency. So these are all going to be point sources, and you can use them across all of the frequencies. Okay, the last calibration method that we talked about, and Dave gave a hint to, are hot and cold loads. The other day, I think Karen also talked about hot and cold loads. We have with W-band and Argus, these wheels that we can rotate a hot load and a cold load or an ambient load in front of. And so you want the difference between, ideally, between that hot and cold load to be pretty large, right? And from that, from looking at the hot load versus the cold load, you can measure the gain of the telescope. And from that gain and the voltage that you're reading off from your observations, you can measure what the system temperature is, what the temperature of your source actually is, right? So this is another way, it's similar to me in thinking about it, to thinking about noise diodes, right? You have something that is on or hot, that's when your noise diode is on. You have something that is not on or cold, that's when your noise diode is off. Those aren't perfect parallels, but I like that image. Something bright versus something faint, comparing the two and using those to calibrate your whole system. Questions here on hot and cold loads? Yeah.
Why would you do this and not just use a noise diode?
Yeah, so I'm going to flip this to Dave. Why does Argus not have noise diodes and instead has hot and cold loads?
Traditionally, at 3 millimeters, the noise diodes do not work over really broad frequency ranges. That sort of changed over time. So it was, so the idea. So in the future, we'll be using noise diodes with like DOBI observations at 3 millimeters, but so simplicity and cost, like Argus, you have to inject those noise signals and all those things. But I mean, the technical reason that the engineers have stayed away from it in the past, and this goes way in the past, the noise diode technology didn't work for broad bandwidths. I don't really think that's the case as much anymore. That motivation's gone away. So people do it historically. Like when we built Argus, it was an exploratory instrument to just prove that they could build the modules. The team that built it didn't even think about the calibration after the fact. They said, oh, we can do something. Let's put a vane over the top. Exactly calibrate. So not a lot of engineering went into that aspect because it was more demonstrating that they could build these modules, but then they designed and mixing in the yellow. So it was an engineering experiment that we leveraged to do science here. Is the way it's supposed to be a prototype. But yeah, I have asked that question. We think we could get noise dials. Maybe not over the full band, like this 3 millimeters is really broad from 6 to
Goes from
6
yep.
down below, and it crosses. This is getting a little technical, but different waveguides. You get these waveguides that work at the lower end of the band, the higher end of the band. And since astronomers, we like the one, CO at 115. That's a different anyway. Different wavelength. So we could make it work. We can get noise dials, I'm pretty sure, that work at the lower end of the band, but then we might need something different way at the higher end of the band at 115 gigahertz. So,
Is the actual frequency of the noise diode important here too? Like, is it harder to build a 100 gigahertz?
in the
diode?
past, I think it was,
Yep.
not now. So that's another aspect in the past. They couldn't build ones that were provided stable noise, like a consistent flat noise across the band. I might be able to reject a signal that would decay off, so it'd be like this way at the. So that's why. That's a good point too. So.
Engineering and money. Right. This isn't really spectral line calibration, but since we haven't talked really at all about pointing and focusing, I wanted to bring this in. At the start of any of your observations, you want to make sure that the telescope is pointing where you think it is, right? So at the start of any GBT observation, you would do a peak focus where you point the telescope at a known quasar, you scan across it, and the system will compare, okay, this quasar should be at this location. This is the location I measure it to be. So I need to change my model so I'm more accurate, so that the pointing accuracy of the telescope is more in line with reality, right? And our pointing model is pretty good, but it is better if you do pointing observations near your scientific targets. Right? So that's pointing. The same thing is true for focusing. You want to take the telescope out of focus, in and out of focus a little bit to sample where you get the peak brightness as you do that out of focus measurement. And then that sets where the focus of the telescope is put. So we recommend that you do these at the start of any observation. Sometimes low frequency observations will skip it because it doesn't add very much to the pointing accuracy at low frequencies, but it is an excellent check that everything is going well in the system, right? You're getting data, it's coming through, everything seems coherent and like the system is all set up correctly. Yeah.
Is that included in the GBT calculator, or is that something you need to specify separate from your observation?
It is separate. So this would be something that you would add in as overhead. Usually at low frequencies, we say 10% overhead, and that includes pointing and focusing and then slewing to your target. Yeah, that'd go in the technical section. Yes.
When you talk about adding this to your model, do you mean your beam model or which model?
The pointing model. Yeah, so we have a model for if the telescope needs to point at array of 1 and deck of -10, where do the electronics have to guide it so that it is pointing there? And so that is natively pretty good. We can get really close, especially at lower frequencies, but at higher frequencies, the model is sometimes just not good enough to get right on the source. So we want to point at these bright quasars to make that correction. Because also specifically at higher frequencies, all of the gain matters, right? You don't want to be even a little bit less sensitive because these tend to be harder transitions to get. The atmosphere is fighting against you, etc. So you want the peak and the focus to be really as good as they can be, specifically at the high frequencies. Recap of everyone. So you should correct your observations for the atmosphere at all frequencies, but it's especially crucial at high frequencies, right? We showed that plot where the atmosphere was doing us dirty everywhere above about 10 gigahertz. Several different observing techniques can be used to give on minus off. We can do frequency switch, we can do position switch. We talked about which of those is probably best for your science. At centimeter wavelength, so lower frequencies, we use noise diodes to calibrate the data, while at millimeter wavelengths, higher frequencies, we use ambient and cold loads, that hot and cold load that we showed earlier. You also should observe a calibrator at least once per semester per target frequency so that you can go in and calibrate your objects. A lot of times people will want to do a quick check on a calibration source in every observation. So it is dependent on you to add those in just so that you can check against the noise diodes that everything is behaving as you expect it should be. So those are the topics we covered in the last 50 minutes or so: atmospheric opacity, spectral line observations, position versus frequency switching, and then how you can calibrate with those different methods. And that is the end. I will point out that there's an old book, it's old book at this point, from 2002 that was based on the first single dish school that was held in Arecibo. It has not been updated since then, and we are taking it upon ourselves to try to update that now. So take a look out on that, but you can find Karen O'Neill's initial lecture on this calibration if you look up single dish radio astronomy techniques and applications. It's a white book that was put out by PASP, and hopefully we'll have that updated at some point over the next couple of years. So I'm going to go back to this recap page and take any questions from you.
Go back to the previous slide.
Ellen,
Okay.
this one?
No, the feed. That one.
Yep.
So focus calibration, how would you change your focus on a radio telescope? I imagine this is like optical telescope, or how you would change it with your.
It's very similar. So the subreflector is moving, it's physically moving. So we're changing the subreflector to change the length of the optical path. So the 20 meter also has that ability, but it's not baked into the Skynet system. So none of you have the ability to set the focus on the 20 meter, unfortunately. But yeah, you're actually changing the optical path.
The reflector is moving or wobbling?
I think it's physically moving.
It's effectively a bubble.
Yeah.
But it's a platform with 6 axes, but it's literally just moving in one direction. So the feeds are in an azimuth or cross cell direction, it just moves it between. So it's like it'd be equivalent of a wobble, but the sun reflector isn't, I forget the name of the platform. It's a 6 axis platform. It can move in all directions.
The whole dish is sort
We're
of.
effectively tilting it back and forth. We're just tilting it, so it's like a wobble.
It's not thought to cause great defocus, I suppose, because it's one moves.
Oh, well, we can move the subreflector in a lot of different directions. So if you're talking about subbeam non, we move it back, tilt it back and forth, put the signal in two different beams. We move that subreflector, maintain the collimation of the telescope as a function of elevation. GBT is completely rigid. As you go down, the feed arm sags. You have to correct for that. Instead of trying to correct the entire surface, which we do, there is surface corrections too. What we do is we correct it via the subreflector by the collimation. So we are constantly changing the focus and pointing as a function of elevation. This isn't even pointing model. We call this focus tracking model, but that's just internal jargon. But the subreflector is being moved around to maintain our ability, both the focus and the pointing of the telescope. And then we have other models on top of that to correct for the pointing. If you look here, we want to go over here. How much do things change? So we have other models there.
There's 6 different axes, right, for the
For the
subreflector.
subreflector, yeah. And we had one of them was broke, it sort of was misbehaving last
ZT,
a year
YT.
ago. Yeah, about this time it was actually, instead of, it was oscillating back and forth around. I wanted to be here instead of going there, it was going here, 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 here. And that, it messed up us being able to do high frequency last year. We got that fixed just in time to have the war break. But anyway, last year was a struggle.
How do you go about calibrating the ultra wideband receiver? That's huge range.
We just asked. We asked for Ryan.
Yeah, Ryan's out there. Ryan, how do you calibrate ultra wideband?
The same method, just basically the same method.
Calibrate ultra wideband with noise diodes across the entire frequency range.
Standard way we do thus far, the receivers.
Okay, yeah, it's the same one. A couple questions online.
All right, with faint objects, what criteria do you use to decide if a scan is worth keeping? For example, the source and the position switching example looks really bad. How do you determine?
Oh, that's a beautiful spectrum. It just depends on, the bandpass shape that you see. Usually for, I mean, if you're trying to go for something that hasn't been seen before, right, it might be a faint transition. So you might need many hours or tens of hours in order to see it. So just building up the sensitivity with many observations. So that observation, if you did the same thing the exact same way and average those two together, you'd have square root 2 better noise. So you would eventually build up a really clean detection. That was probably like a 2.5 sigma detection. If you wanted 4 sigma, you're gonna have to observe a bit longer. Yep.
In the atmospheric correction, that's wrong. Is nodding only useful for galactic surveys, or is it also used for the compact objects?
Compact, like extragalactic, or I would think that
I missed the question.
is nodding only good for galactic or extragalactic as well? I would think that it's fine for extragalactic. Yeah.
The nodding, the big thing about nodding is the source needs to be smaller than
the beam,
separation. So if it was sort of bigger than the 2 beam separation, nodding doesn't help because you're never off. So galactic people go for point sources all the time. It's used for extragalactic, obviously small sources as well.
Great. When you calculate T-sys from TCal, the terminology on and off is referring to the diode modes and not position switching, correct?
When you calculate T-sys from TCal, yes, it's whenever the diode is on versus when the diode is off.
And we miss our terminology. We go on off when we talk, I do source on off, but then sometimes we're in context, we noise diode.
The noise diode
So
on,
I
yep.
apologize. So sometimes we do sig ref and then on off. So you see sig ref, that's source is a sig ref, that's the blank sky off, on off would be the noise diode on off. Most of our slides that adopt that terminology.
You have another?
Yeah, let's see if there's one more interesting before.
Karen.
Point and focus, like we do that for like pulsars also, right? Not just spectral things.
Yes. Yeah, the recommendation is to do that for all observations. Again, even if you don't need it to correct for the actual peak focus, it's a really good system check that balancing is going okay, that all the system is behaving.
In the atmospheric correction equation, are the zenith angle and elevation measured with respect to one's horizon? What?
Yes, so the elevation is measured with respect to horizon. Let's bring this back. Elevation is measured with respect to horizon. Zenith is respect to straight up. So if you're looking straight up, cosine of z would be cosine of 0 in this equation. And down here, it would be 90 minus 0. Right? It would be sine of 90 for straight up, which should be 0. Oh no, should be 1.
But for the case of L band, this is not necessary.
For correcting atmospheric opacity, I've not corrected atmospheric opacity at L band. You should. We do recommend that you should. You can look it up. It becomes more important above 10 gigahertz, but it's important across the entire frequency. I should say I've never observed at L band, so that's why I've never corrected. Yes.
So is the peak focus calibration separate from the known calibration source from a GPT perspective? Do you actually have to specify both, or are they part of the same one?
So I've seen people do an on-off on a calibrator. And that's separate from their peak focus. So, yeah. You might also, instead of looking at a known calibrator, you might have, if you're observing ammonia or a water mazer or something like that, you might want to observe a known ammonia source of really well-defined temperature so that you can compare that temperature you measure to the temperature that you measure, right? If you see that it is the same as it is in the literature, that's a good check against your observations. Or if it's not, you can scale. Yes.
So I have another one online. So if you're taking observations, is it better to do 3 separate shorter observations to average together or a longer observation?
It probably depends. I would err on the shorter observation. Well, it depends on how long short is. So you don't want to do an observation, I would say, of a track of say 40 minutes or something like that. I would want to break that up into smaller ones and average together. For pulsars, it's a bit different, right? I see Ryan raising his hand. Go ahead.
We're often interested in making sure that we have observations which are coherent in all states. So if you have interruption in the observation, it's generally undesirable. So we'll do observations 8 hours long sometimes and not break them up. But I think the main reason you might want to break them up is to do like focusing corrections or to rebalance the system if you're observing over a wide range of zenith angles or elevations and you have some change in opacity or something like that. So I would say that it's a bit dependent on the frequency that you're observing at, kind of the elevation range you're observing at. Because even if you have a very long observation, your iteration on frequency with which you're writing data out of this will be much shorter. So
correct. So you still save all of that data.
yeah, if there's RFI or something like that, you go remove. It's not like you're wasting an entire 4 hours of data if only a second it's blasted by RFI as long as your integration times.
One addition here is that if you're doing continuum observations, you want to make those as quickly as possible, like Dave was talking about. So if you're trying to make a little continuum map and you need 40 minutes of sensitivity on that object to reach your needed sensitivity level, you want to break that up and do that same map just as fast as you can, maybe 5 times in that 40 minutes, and then average those together. And that is because of gain variations like Ryan was talking about.
I'll just jump in in terms of how often how long your integrations are, it's a function of frequency, but the pulsar is just a track. But at the higher frequencies, your on-offs matter. So your sky is changing, so you don't want to spend, like at L band, you can spend 5 minutes or 10 minutes on and a minute off. But at higher frequency, when you switch every 1 to 2 minutes on off, so the sample is off. So that can drive the scan times.
Any other questions in here? Yeah.
Is there any reason why we go for scan averages as opposed to medians or modes?
You mean how the GDT they do it?
Or I mean anybody, because I've noticed that everybody just says take a bunch of stuff, average it together.
Averaging is going to reduce your noise level, whereas median
reduces noise level.
So
is it by the same amount?
It's more robust. Median's more robust. So I do a lot of stuff with median. I do a lot of median filtering, but you're correct in terms of how radio astronomers traditionally average combine data together. They do weighted averages, and it's based on the system temperature and the integration time. They're effectively assuming there's no outliers. That other than effectively. So but yeah, there are potentially more robust ways to combine data than a straight average. I would use like a median and absolute deviation. These are bad tech data. That's just my personal preference, but
yeah, good question. Any other questions in person?
Well,
No?
I guess I'm planning on working on L-band. So I'm thinking of RFI. That quantitative approach on the way to actually carve in, or the quality control, I'm not familiar on. How do you go through then to see which scans happen in that? Is that totally manual or?
It's, well, right now it's pretty much manual, although we're developing routines that are going to be able to go through and excise RFI. So Ryan actually is working with some of those right now. Real-time RFI mitigation versus manually going and seeing it. So if you go in to your longer scan and see that there's RFI, that might be only in 1 second of that integration. And if you're saving your data every second, then you can salvage that just by getting rid of that one observation. But we've had a lot of work over the past couple of years on how to automatically identify those sources, because they look different than astronomical sources. And Ryan could talk about this, but there's different kurtosis or shape of the RFI signal than what you typically think of as Gaussian sources for astronomical signals. Now, if you're looking at satellites, that might be a different question. Do you want to say anything, Ryan?
We'll just contrast with some research that we're doing, potential ways of trying to do this in real time, but I don't think that's imminent versus you're asking about manual. I mean, you can also do statistical tests of your data after it's been recorded to try and automate flagging, and depending on the observing mode that you're in, that kind of thing. I don't think there's a ton of that in GPT-IDL. I think there are plans to try to incorporate more of that Python replacement. There are some community supported packages that do this. There's a lot of robust tools for doing this with Pulsar data, and there are all different ways of looking at statistics and trying to find outliers.
Any final questions? Ren online?
Yes. In the frequency switching technique, what is meant by switching T1 minus T2 and T2 minus T1 patterns, and is it averaging over frequency?
So that T1 that I had listed there was the epoch one or time one. So this is an observation at one time. This is a second time, just a little bit later, when we have used the LO to switch where that line is. And then, yes, we are doing the subtraction between these two scans in two different ways, T1 minus T2, T2 minus T1, shifting so that this line overlaps between the two observations, and then averaging them together. Okay, with that, if you do have any other questions, find me, Dave, any of the other folks around, but we are going into coffee break right now. Let's go until 35. And I'll give you a little teaser for tomorrow's schedule. You have in-person tours of the machine shop and electronics lab at 9. So we can meet at the entrance to the Jansky lab right around 9, a couple minutes before 9, and then we'll split into 2 groups for that. So enjoy your coffee and enjoy your 20-meter observations.